Good morning. It's my pleasure to present a paper, What Makes a Good Movie Recommendation? Feature Selection for Content-Based Filtering. My name is Maciej Gawinecki and I did this research together with Wojciech Szmyd, Urszula Żuchowicz and Marcin. We all come from Samsung R&D Institute in Poland. To give you a brief context of our research, let me explain what content-based filtering is. It's a technique that uses item features to recommend other items similar to what the user likes based on her previous actions or explicit feedback. There are, however, situations when user profile or browsing history is not available and the only information we have is the item user selected. In such situations, we can recommend items similar to the selected one. For instance, songs of same genre or movies where the same actors played. This approach is called more like this. In the following example, you can see that a user is watching a trailer of a black comedy movie. On the right-hand side, YouTube has recommended another videos of similar topics. No information about user has been used because the user is not signed in. Here we have an example of two movies that many users find similar. But what features make them similar? They have been directed by different directors, Scorsese and Tarantino, have different casts, De Niro and Travolta, and have scenarios written by different writers. However, they are both crime drama about drugs, so in this particular case, they share similar genre and category. The important thing here is that we can use multiply features together to assess similarity between two movies. To define how much each feature contributes to this similarity, recommenders use feature weights. The example from the previous slide inspired our research. In general, we were interested in two types of questions. First, which features gives best recommendations? For instance, are movies directed by the same person more similar than movies written by the same writer? And second, which representation of a feature returns best recommendations? For instance, is it better to represent textual features such as movie plot as universal sentence encoder or as doc2vec embedding? Answering such questions boils down to selecting right features and their representations, and can help in lowering licensing and computation costs. It can also help in getting better recommendations. To answer our research questions, we have evaluated a number of recommenders in offline setup. There were 4 moving parts that we changed from one recommender to another: features, their representations, distance metrics between those features, and feature weights. Each recommender generated 5 recommendations for each selected movie. Performance was measured against groundtruth ratings using 2 metrics, precision and coverage. Groundtruth ratings were collected with crowdsourcing. As you can see, for precision, we considered only labeled recommendations, and hence the denominator of precision can be sometimes lower than 5. In particular, this happened when annotators could not agree whether it is a good or bad recommendation. To quantify percentage of missing ratings, we reported also coverage. Obviously, offline evaluations are less realistic than online evaluations. To make it as realistic as possible, we defined annotation task as part of real recommendation situation. Here, each annotator was asked, would you be interested in watching the recommended movie given the movie you were searching for? And here is a screen that they were shown and the scale that they use to rate a recommendation. On the left-hand side, you can see a movie user searched for, and on the right-hand side, our recommendation. Each movie pair was rated by 2 annotators. In case they did not agree, we asked third annotator to decide. So how did we select pairs of movies to submit for rating? Our movies dataset contains over 20,000 movies. This makes up almost 200 million possible movie pairs, which is enormous to rate manually. Since we have 9 features, we could rate only recommendations generating using all possible feature subsets. Those recommendations would be generated for a small but diverse set of movies. But again, this still means rating around 400,000 movie pairs. To cut the budget, we borrowed from information retrieval an approach called iterative pooling. We generated recommendations for initial combination of 9 features with equal feature weights. We submitted recommendation to the crowdsourcing system, and then the collected ratings were used to find next recommender to evaluate, for instance using SVM classifier or other approaches we will discuss later. We always submitted only recommendations not rated yet, and collected ratings were added to the existing dataset. So our dataset was growing from one loop to another. As a result, we have spent budget only on around 15,000 annotations, getting ratings for around 5,500 recommendations. We evaluated how choice of representation for a feature impacts recommendations performance. Here you can see results only for 2 of the analyzed features, both textual, movie summary and plot. First, we evaluated recommenders with all features, changing only representation for summary and plot. And next, we analyzed recommenders with only one feature, one with summary and another with plot. What you can see is that universal sentence encoder performed best. Results for doc2vec were not conclusive due to a very small coverage. We also asked which feature is more relevant. To assess relevance, we employed 3 feature weighting methods: support vector machines coefficients, relief filter method, and mean decrease impurity. We tested 3 different methods because usually there is no universal feature weighting method that works for all possible configurations. The chart shows that most relevant features were summary, category, plot, and gen. To make sure obtained feature weights generate better recommendations, we measured the precision against recommender with equal weights for each feature. Precision of recommenders with weights optimized by all methods are similar to each other and exceptionally higher than in the equal weights scenario. To confirm previous findings, we have evaluated also recommenders with only single features. You can see that 4 previously identified features performed best. Finally, we ask if some features are redundant. In other words, they do not improve performance. To find optimal subset of movie features, we run recursive feature elimination algorithm with SVM classifier. You can see that it is enough to have 5 of 9 features to get recommendations: genre, plot, summary, category, and release year. All other feature subsets had lower classification precision. Once we got the optimal subset, we trained SVM classifier on it to get optimal weights. We used those weights to generate new recommendations, get missing ratings, and evaluate. The result confirmed that performance without features such as direct or language or popularity is very similar to the performance of recommender using all features. To summarize, in our work, we asked which feature representation gives best recommendation. We found that using universal sentence encoder for movie summary or plot offers best recommendations. We analyzed which features are most relevant in the movie domain. We also asked which features combinations gives best recommendations. We found we can reduce number of features from 9 to 5 without losing recommendation performance. This can save computational and licensing costs. Finally, we have collected large dataset of movie recommendations ratings. We publish 30% of the dataset online to encourage further research in this area. Thank you very much for your attention.